Historical development of periodic classification of the elements. Dobrnier's trade. Imagine you have a collection of 50 different random objects. Your job is to organize them. How do you start? In the early 1800s, scientists knew about 50 different elements. They were like a giant, disorganized pile of puzzles, pieces with no picture on the box. There was no system. A German chemist named Johann Wolfgang Dobrner, 1780 up to 1849, was one of the first people to find a fascinating clue. Dobrner noticed that certain elements could be grouped into sets of three that had very similar chemical properties. He called these groups trades. He found a mathematical relationship in each trade. The atomic weight of the middle element was almost exactly the average of the atomic weight of the other two elements. Middle atomic weight is equals to atomic weight element 1 plus atomic weight element 3 divided by 2. Consider the following examples. Consider the alkali metal trade, lithium, sodium, potassium. Atomic weight of lithium is equals to 7, atomic weight of sodium is equals to 23, atomic weight of potassium is equals to 39. The middle element of sodium is equals to 7 plus 39 divided by 2. It is equals to 23. The calculated average 23 matches the actual atomic weight of the middle element sodium. It is perfect result. Example 2, consider halogen trades. Chlorine, bromine, iodine. Chlorine is equals to 35.5 and bromine atomic weight is 80. Iodine atomic weight is 127. Then bromine, the atomic weight is equals to 35.5 plus 127 divided by 2. It is equals to 81.25. According to Dobrner, the calculated average 81.25 is very close to the actual atomic weight of bromine, that is 80. It is not perfect, but it is remarkably close for the tools he had available. Example 3, the alkali earth metals trade, calcium, strontium, barium. Then strontium is equals to atomic weight of calcium plus atomic weight of barium divided by 2. 40 plus 137 divided by 2, it is equals to 88.5. The calculated average 88.5 is very close to the actual atomic weight of strontium 88. Example 4, consider sulfur, selenium and tellurium. Selenium is equals to atomic weight of sulfur 32 plus atomic weight of tellurium 127.6 divided by 2. It is 79.8. It is very close the actual atomic weight. The actual atomic weight is 79. Consider limitations of Dobrner trade. Only a few trades worked for the many other known elements. This pattern did not fit at all. Consider the following example. Iron, cobalt, nickel. Cobalt is a middle element, then the sum of iron atomic weight and nickel atomic weight divided by 2. The actual atomic weight is 58.9, but the calculated one is 57.25. The calculated average not match the actual atomic weight of the middle element. The pattern was incomplete. Let's take iron, cobalt, nickel. These have no the same property, but grouped the same group. The other is Newland's law of octaves. In the 1860s, an English chemist named John Newland decided 56 elements arranged in a single list by increasing atomic weight. How many of you are familiar with the musical scale? Do, re, mi, fa, sol, la, ti, do. Musical note do repeats at the 8th note in a scale. Re repeats at the 9th note in a scale. Mi repeats at 10th in a scale. Like musical scale, Newland noticed that when he arranged elements by atomic weight, the first and 8th element had similar properties. The second and 9th were similar properties. The third and 10th were similar properties. He called this pattern the law of octaves. Consider the following elements: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine in one period. The other is sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, the second period, and the third period is potassium and calcium. According to Newland, the first lithium and the eighth sodium have similar properties. The second beryllium and ninth magnesium and 16th calcium have similar character. The third boron and 10th aluminum have similar character. See, limitations related to Newland's law of octave. Filled with heavier elements. No place for new elements. The discovery of novel gases completely disrupted the pattern of octaves. Unlike elements, iron and oxygen were grouped together just to fit the rule. The other is Mendelev's periodic law. Russian chemist Dmitry Mendeleev published a short periodic table which consisted of only 63 elements. Inert gases were not included as they were not discovered at that time. These elements were arranged in 7 horizontal rows called as period and 8 vertical columns called as groups. Some vacant like were specified for undiscovered elements and their properties predicted. See, the following 2 elements predicted their character and the position left by Mendeleev. Those are Ica aluminum and Ica silicon. Ica aluminum, this time known as gallium. According to Mendeleev, Ica aluminum predicted the following character. It predicted atomic weight, it is 68. Predicted density is 6 grams per centimeter cubed. Predicted it would be a metal that forms a sulfide and an oxide. And gallium can be discovered. The actual atomic weight of gallium is 69.7. Actual density of gallium is 5.9 grams per centimeter cubed. It was a metal that formed gallium sulfate and gallium oxide. Predicted result and actual result almost similar. The second predicted is for Ica silicon, or this time known as germanium. Predicted atomic weight is 72. Predicted density is 5.59 grams per centimeter cubed. Formula oxide is EO2. Germanium, this time actual atomic weight is 72.6. Actual density is 5.323 grams per centimeter cubed. Formula oxide is GaO2. Almost similar. Let's see limitations. Position of isotopes because he depend on atomic weight. Anomalous position of some elements. Periodic. Generally, Mendeleev's periodic law states that the physical and chemical properties of elements are a periodic function of their atomic weight.